Okay, sorry for the delay in that case. So as I said, I'm Karel Devriendt. I'm at Oxford University and Alan Turing Institute in London. And the work I'll present is done together with Renaud Lambiot, my supervisor, and Mark, who's soon starting his PhD at Warwick University. So the title here is Nonlinear Network Dynamics with pitchfork bifurcations. But actually, I will talk about something slightly different. So mainly about the first part and only briefly touch upon the second part, which is because we found some new results lately that I prefer to highlight more than these things that we found earlier. So I'll talk about network dynamics, as many people have done before me on this conference. So just to make sure that we all know what specifically I'm meaning, I'll introduce the setup. So for me, a network will be an undirected connected graph, so one as drawn here. And then the system is, or the dynamics are defined by assigning a dynamical state xi of t to each of the nodes. Right? So there's this real number to each of the nodes, so that the state space is like Rn if you have n nodes. And then the dynamics are defined on a network like that by saying that so there's a differential equation for each of these states, and it depends on its own state and possibly also the states of its neighbors. Right? So we have this system of differential equations, which is somehow constrained by this network, and that's the network dynamics then. And so the question I'll look at is, how does the network structure influence the dynamics? Right? So you can think of it locally, there's a small system going on, but there's many different ways in which you can interconnect this system to form like a global system. And then the question is, how does a specific interconnection pattern influence the dynamics? To sort of start with an easy example, we have this classic system that is diffusion dynamics, where the change of state xi is dependent on the difference with its neighboring states. And then as a result, we'll see that all the states in the end will converge to the same value. So just to get an idea of what that looks like, for the graph here on the right, we assigned as an initial state just a random value between 0 and 1, and then we run this system, this diffusion system, and in the end we see that there's exponential convergence to a fixed value that's equal actually to the average value of the initial state. So this is also sometimes called the heat equation, because if you would imagine that each node has a certain temperature, then if there's a difference between two nodes that are connected, there's going to be like a heat flow from one to the other until all the temperatures are sort of balanced out. So some direct things we can say about this system is that it's a gradient system. So you can define a potential in this way, and then the system follows a negative gradient of that system. And as a consequence, we know actually that there's always going to be a decreasing potential, and thus the system will converge to stationary states, which are local minima of this potential sort of landscape on a state space. Secondly, as I mentioned before, the stationary state is one where all nodes have a constant value, fact which is equal to the average of the initial state. So that's x0. And for that reason, it's sometimes also called consensus dynamics. Right, and from this perspective, it's actually used sort of as a paradigm system for many real-world systems where distributed consensus is something that's observed. Right? An example is biology, where in a school of fish, like fish only can locally see their neighbors, but still the whole school moves in sort of a smooth fashion. And then the question is a bit, how do these sort of global observables reach the individual or the knowledge of the individuals in the system? And then in this system is one example where there's only locally exchange of information or of state information, but then globally you reach something that's a global consensus state. And then there's other examples in like engineering or social systems where there's coordination of agents in the system. How do you start to sort of study a system like that? Well, one way to go is to introduce the Laplacian matrix of the graph. For those who don't know it, it's so if you have n nodes, it's an n by n matrix. Each row and column is corresponding to one of the nodes. And then on the diagonal, you put the degree. So D has degree 4 for neighbors. E has 2, etc. And then on the off diagonal, you put a -1 if there's a link So for instance, between A and C, there's a link, so you put a -1, and that way you fill the whole matrix, and that's the Laplacian matrix. And so the reason why it's useful in studying dynamics, or diffusion dynamics in particular, is because you can rewrite the system in this way. So as a linear system with a negative Laplacian, and then the solutions just look like this with a matrix exponential of the Laplacian. And then so from linear system theory, you just know that the spectrum of this Laplacian matrix will tell you a lot about at least the qualitative properties of your system. And that's one way in which we can use structural information to say something about dynamics, or the first example, because we know from spectral graph theory, that's the field of study where we look at matrices, all sorts of matrices that are assigned to graphs, and then we study their spectral properties. And there we know, for instance, that for a path graph, the smallest eigenvalue will be typically small, while the largest eigenvalue is typically large. No, sorry. Well, for this graph, the smallest eigenvalue is typically large. And so that's something you know purely from looking at the structural properties of the graph. And then you can translate that to what you expect will be dynamical properties of diffusion in this case. And you see here some examples of diffusion dynamics. Here it's a slow behavior, while here you have very fast convergence. And so in our work, we sort of found similar results where you translate some structural things to dynamical things, but for a more complicated system. And so what are we looking at? We're looking at a nonlinear generalization of consensus dynamics. So if you're trying to model real-world systems, you'll know that very few systems are actually linear, and there's often more going on than simply reaching consensus. Right? And this calls for some sort of generalization, and in particular, you can think of nonlinear generalization of the system. So what we specifically looked at is this proposed framework by Srivastava, Mullis, and Bullo, where they say they propose to introduce some odd function f into this system, and then there's different places where they say you could add this nonlinearity. So first you could add it at the level of single nodes. You could add it at after taking the whole sum of the differences, or you could take it at a difference itself. And then the first result they found is that it's this sort of notation or this form where Q is again the Laplacian, F is then sort of an entry-wise function, and this is a composition of these two functions together. And similar for the second system, but for the third system, they didn't find a notation of that. And as a result, they actually found a lot of characterizations for these two first systems, but the third one, sort of only for small toy examples, they could say something about the properties of the system. And this is what we'll be focusing on here in the talk and in our papers as well. So a first step, we'll introduce another matrix. So this is called the incidence matrix, and it has so that each column is corresponding to a link, while each of the rows is corresponding to a node. And what it's encoded here is, for instance, for link 3, the neighbors of that link are C and D. And so that means that for column 3, you will have 1 and -1 here, or the other way around, -1 and 1. That doesn't matter. You see, for each link, you can just say which two nodes it's connected to, and you put that information in the matrix. So the reason why we introduce it is actually because there's a connection between these two matrices. So the Laplacian can be written as D transpose. And this actually allows to unify the three cases of nonlinear consensus dynamics that were proposed, where now the third one also has a nice sort of decomposition of this form. And so, well, there were results for these two based on this easy form. We'll now use this form to also get extra or get results in this case. Another cool thing is actually that you can now think of this third system as a system that takes place in the links. And so if you take this D transpose X, you actually take, so then you get a new variable, let's say it's Y, which actually just equals to the difference between two node states. And then you can actually just rewrite the system this way, so by multiplying with D transpose both sides. And so then you can think of it as a system that has its variables on the links and then is constrained by which other links it shares a node with. And so that's a different way to look at it, at the same system. And well, I won't give specific results we have from this, but in the end, I'll give one small hint to like how this could be used to further generalize some results we have. Okay, so I've been calling it generalized consensus dynamics, but actually maybe we break everything about the consensus dynamics by introducing this nonlinearity. But well, luckily we don't, as I will show. So it's still a gradient dynamical system. You can still formulate a potential function, which now has this antiderivative f at each of the links, right? So you have a sum over the links, or for each link, it's then a symmetric function of f, and then your system follows the negative gradient of this potential. Second, it's still a consensus dynamic because the constant state is still a stationary state of the system. Right? So if you let the system evolve long enough, it is possible that you will reach again the consensus state. However, and luckily maybe, there's also more stationary states in the system, right? Because we added some complexity to have maybe more modeling power to the system. And one thing we get is that there's more stationary states. So how do we understand that? So the change of x is dependent on this sum of the differences. And if we want this to be 0, somehow we need to solve this, which is a system of n nonlinear equations, if you have n nodes. But another way to do it is to just simply say if each of these contributions is 0, and also the total sum will be 0. And that's sort of the set of solutions. Right? So an x for which all differences over the links is one of the roots of f. And here, so maybe an example to show that for a simple cubic coupling function f. So here there's 3 roots. There's -1, 0, and 1. And so that means that if the difference of x over links is equal to -1, 0, or 1, then we'll have a stationary state. So here I give an example where that's the case. So here x has value -1 and 0. So there's a difference of 1 or -1, if you will. So that's okay. Difference of 0, 0, 0, difference of 1, 1. All of these are equal to one of the roots of f. And just the total will give you a stationary state. Another way to encode this is just to say, to give each of the roots a color. So these two, because it's, well, you can change the sign, they're the same. So you'll give that color red, and then the one at 0 gives color black. And you can encode a stationary state by coloring the links of your graph. Okay, so that's nice. There's extra stationary states, but what about their stability? So is it something we might observe in the real system, say in presence of noise? So for stability, we can use linearization. So a small excursion from a stationary state, and then the system will evolve based on the Jacobian of your system. And then you can calculate it by the chain rule, and you'll find it has this form of the instance matrix and some diagonal term, which is actually equal to so f prime is a derivative of f with respect to x, and then d transpose. And what this looks like actually is it looks a bit like a Laplacian matrix. Right, so f prime, so at each of the roots we look what the derivative is. So here it's -2, here it's 1, here it's -2 again. And then these values, we put them on the links with the appropriate color. So the red ones will get a -2 and the black ones will get a 1. And then the Jacobian is simply the Laplacian matrix of these link weights with possible positive or negative weights. And so what that means is actually our Jacobian can be written as a difference of Laplacians. Right, so if you think of all the positive links and all the negative links separately, then your Jacobian is something like the difference of these two Laplacians. Right? So, for instance, here we have a graph. We colored the links in 2 colors. That gives us 2 subgraphs, so positive links and with negative links. Each of those will have a Laplacian, and the Jacobian for the stationary state, which gave us this coloring, is then determined by the difference of these Laplacians. And so then stability is determined by the eigenvalue of that matrix we just constructed. But what it really means is actually that we're thinking about which of these 2 Laplacians is dominating, right? Because locally around the stationary state, the system will evolve like this, where this is a positive thing, this is trying to drive the system to instability, while this one is is negative, and so goes to stability. And the question is more or less which of those two is more dominant. And so that's actually, if you just look at this question, it's a question about algebraic graph theory, right? Something about eigenvalues of matrices. And so in a sense, our contributions are in technical sense are about algebraic graph theory. But the interesting thing is that they have this direct influence on stability of these dynamical states. Okay, so first result will be based on effective resistance, which is somewhat surprising if you already know what it is. So if you don't know what this effective resistance is, actually it's a distance function that determines the distance between the nodes of a graph. And so it says that for any two nodes you pick, it says, are these nodes far away or close to each other? You can calculate it like this, but that's not really important. What's more important is to understand that it's sort of gives you a full graph view of whether or not two graphs are closely connected. So in this example, we're looking at the distance between these two. So there's a single link. You could say, okay, they're rather close, but if you compare it with this graph, here you also have many parallel alternative paths going from one node to the other. So this will actually give a decreasing distance, and this is an even smaller distance because there's many more alternative paths. So in a way, the nodes are better connected. So there's a lot of things known about this effective resistance. There's relations to random walks, graph centrality, graph embeddings. And in a sense, it's surprising that they appear in dynamics, but I've seen at least one other talk during this conference where people have found resistance or the effective resistance to play a role in dynamical features. So somehow there is this relation based on, well, the fact that this comes down to something with the Laplacian matrix, that there is a relation between effective resistances and dynamics. Okay, and so how does it specifically come into play in our case? So I said that stability is always about how this positive link subgraph is related to this negative link subgraph, right? Like which of both is dominant. But then dominant is very abstract in the sense that if you add them together, they give a positive over negative Laplacian eigenvalue of the Jacobian. But this gives a very sort of quantitative result for that. So it says that if there is a pair of nodes, I and j, such that in the positive graph, the resistance is smaller than in the negative graph. And so what that means is if there is two nodes that are closer together or more connected in the positive graph than in the negative graph, then your state is unstable. And that will mean that that pair of nodes will give you an unstable direction in your Jacobian. Right? And so here's the example from before we visited. So we get this positive subgraph, that's all the black links. And we see here, for instance, that between these two nodes, there's a resistance of 1, while in the red subgraph, there's a resistance of infinity because they're disconnected. And so that will tell us that this sum of two Laplacians, when you write it down in a Jacobian, you actually get a positive eigenvalue and thus instability. Right? So but this is sort of a very tangible way of testing it. And even more so if you're familiar with the effective resistance. And it's still surprising, but it gives you very sort of hands-on way to calculate it. And here's another example that we saw. So there's two subgraphs, and then I show some resistances where these two are fine. So they're larger in the plus graph than in the minus graph. But here there's a case where omega is 2/5, while here it's half. And so this is smaller than that, and the state will be unstable. Right? And the state is represented here by the colors of the links. Okay, so that's something quite neat, I would say, especially if you're familiar more with the graph theoretic notions. But also just the thinking, if you would start from the question, if I put together a bunch of sort of unstable states and stable states, when would they be globally be stable or unstable? That it really is determined by the way in which you do it, and that this way is encoded by the resistance. That's something quite remarkable, I find. So that was an unstable or an instability result, but we have also stability results, and we're over a tight condition. So I've left out the details here, but it more or less says that. So if you have a single positive link, so a single sort of thing that tries to drive your system to instability, then you can determine whether or not this is unstable or stable by saying whether it's smaller or larger than a single value. So there's a critical, so I've written alpha here, but for instance, if you take a particular system, you can get a value for that. So alpha would be 2/3 for this system. So what it means more or less that if, so say this is my single positive link, and I want to see if my whole system is stable or unstable, then you just need to calculate the effective resistance. So here it will be 1, so that's not good. But then you can add more and more links in parallel to decrease the effective resistance until at a certain point you will reach stability. I think this is sort of intuitively interesting because it says that you can create a stable global state by just adding other stable things as long as you add them in the proper way, and the proper way is then encoded by effective resistances, which is again surprising. So I see I'm almost running out of time here, so I'll go a bit over the next thing. So this is a conjectured result, so we're not sure about this yet, but just to say that we think that there's also a way to encode the stability based on spanning trees, right? Which is again like a nice global feature, and there's results that relate to effective resistances. Then another sort of very nice general idea is that the dynamics we look at, so this third case of the nonlinear dynamics, that they actually decouple at cut vertices. So a difficult graph like this, you can actually just look at these smaller subgraphs, smaller motifs to understand what happens in the bigger graph. Finally, well, as promised in my title, but not delivered until now, that we actually also look a lot at bifurcations. So that's in one of the papers where we find that so this simple pitchfork bifurcation, if you add a lot of them together in a network, you get very interesting sort of pitchfork bifurcation-like features, which then depend on the structure. So quickly to summarize, so I've talked about this generalization of consensus dynamics, which still has a consensus state, but also extra things, so extra states. Then given some hopefully interesting examples of how dynamics and structure are interrelated, and with this specific role of the effective resistance, that's rather surprising. And then one more small thing I want to touch on. So it's quite a general result we have here, or a general setup at least. And at least what I would like to think about is how this might be generalized to systems where you have, on a link, you don't have just the difference between two nodes, but you have a d-dimensional system, which then shares some of its variables with other links that are connected. Right? So you sort of see what goes on. And then one way to possibly model this would be via higher order networks or simplicial complexes, where I've had like some preliminary results and interesting things that seem to generalize the things I've talked about now. Okay, so thank you for staying with me. And then I quickly want to advertise, these are the two papers I talked about. So this one is more talking about bifurcations and has more like a network sciencey approach, while this is much more rigorous in the dynamic sense as well, and will be on archive hopefully by the end of the day. Okay, so that was it. Thank you very much.
Thank you, Karel.
Yes.
So, thank you for this talk. Do we have any questions at the moment? I see that we don't. So, I see that we have 20-something participants. So if any of you has a question, you know that you can write it on this question and answer session, and then it will come up. Meanwhile, well, I could just maybe ask, so you've given it, I was going to ask you how you would generalize it, but you already did that at the end. But,
yeah.
What about applications of the generalization? Have you got any particular applications of that in mind for what it might be interesting or useful?
Well, applications not in the sort of real world sense, but like mathematic applications I've thought about more.
One could take it either way, so I don't mind.
Yeah, so in the sort of the more theoretical sense then, well, for me personally, it would be sort of a principled way to also define dynamics on these higher order structures like simplicial complexes. That's something that, well, I've been reading several approaches and they all start one way or another, but for me, it's like a sort of a nice clear-cut way to start with them is to define a potential function and then look at the gradient dynamics of that, and that would be a direct generalization of what we do here. And so it's in that setting that I found some preliminary results which seem to mimic the things we've had now, where Hodge Laplacians take the place of Laplacians, and then you go around the spectral theory of those Laplacians to see whether or not you generate. So I've not had those results, but it seems that that's like one way forward that I would be interested in.
Mm-hmm.
It could be done for Hamiltonian dynamics potentially as well. So that would be one way where, well, in a sense, generalization is just this sort of where you use this incidence, then a nonlinearity and another incidence matrix. That's more or less a thing I would generalize then to their corresponding boundary operators on higher order objects. But that's more of a wish than a reality at the moment. Yeah.